Two models. Same task. Same data.
Model A, 99% training accuracy, 61% on test. Model B, 81% training, 79% on test.
Which one would you have shipped? That question is what this episode answers. Episode 18, the Bias-Variance Tradeoff. Why a higher training score can be a warning sign, not a win. Underfitting, your model is too simple for the pattern in the data. A straight line trying to fit a curve. It just can't.
Training accuracy is low. Test accuracy is also low.
Both scores bad at the same time, that's the signature of high bias.
The model didn't even learn the training data well.
Overfitting, your model is too complex for the data it's given. It doesn't learn the pattern, it memorizes every point, including the noise.
Training accuracy, near perfect. Test accuracy, falls off a cliff.
A big gap between train and test is the signature of high variance. Both failure modes come from the same trade-off. Plot error against model complexity. Training error always drops as complexity increases. Test error does something different, it forms a U-shape.
Too simple on the left, high bias. Too complex on the right, high variance.
Somewhere in the middle is the sweet spot, the lowest point of that U.
That's the model you actually want to ship.
Learning curves plot score against training set size, not complexity. Train the same model on 10%, 20%, up to 100% of your data.
Plot the training score and the validation score at each size.
If the gap between them closes as data grows, that's a healthy sign. Sklearn's learning_curve function gives you exactly this plot. You can read the diagnosis straight off the curve shape.
Both curves flatten out low, close together, that's high bias. A wide gap between train and validation that never closes, that's high variance.
Flat and low means add complexity. Wide and open means add data or simplify the model. In code, this is one import and one function call. Call learning_curve, pass your model, your data, and a CV object. Give it a list of training sizes, sklearn handles the rest. Average the scores across folds at each size. Plot training score and validation score. The gap is the diagnosis. If this clicked, subscribe. Feature engineering is next. Let's fit 3 versions of the same model on one dataset. Degree 1, too simple, train 0.61, test 0.6. Degree
15, too complex, train 0.99, test 0.58.
Degree 4, balanced, train 0.85, test 0.83.
Same features, same algorithm family, only complexity changed.
Degree 4 is the one that survives cross-validation. Once you know which one you have, the fix is specific. High bias. Use a more complex model, add features, reduce regularization. High variance. Get more data, simplify the model, add regularization.
The fix always points in the opposite direction of the problem.
How do you know which one to worry about? If your training score is already low, that's bias. Grow the model.
If training is high but test lags far behind, that's variance.
Small dataset with a complex model, variance risk is elevated. Huge dataset with a simple model, you're leaving accuracy on the table. Unsure which one you have? Plot the learning curve. Don't guess. Get quick recap before we go. Underfitting, model too simple. Both scores low. Overfitting, model too complex. Train great, test falls apart. The trade-off, test error is U-shaped against complexity.
Learning curves reveal which one you're dealing with.
The sweet spot, small gap, both scores as high as the data allows. Where we are in the series. We can now evaluate a model honestly and diagnose why it's underperforming.
Episode 19, Feature Engineering, turning raw data into ML-ready data.
Scaling, encoding, missing values. We'll build it from scratch. Episode 19, Feature Engineering Explained. Feature scaling, standardization versus normalization.
One-hot encoding, turning categories into numbers.
Handling missing data the right way inside a pipeline. Subscribe so you don't miss it.
Your challenge task for this episode.
Load any regression or classification dataset. Train a too simple, a balanced, and a too complex version of one model family. Record train and test scores for all three.
Plot a learning underscore curve for the balanced model.
Label the underfit and overfit regions yourself. Bonus: use Grid Search CV to find the true sweet spot and compare it to your pick. Solution is in the repo. Think before you look. Model A had 99% training accuracy. It was overfit.
Model B, 81 train, 79 test, was the sweet spot.
Ship the model with the smaller gap. Episode 19 Feature Engineering drops next. Subscribe. Comment below. Have you shipped an overfit model by mistake before?